right, thank you for inviting me, and it's a pleasure to be here. So I think I got invited because I used to work on domain adaptation. This talk is sort of going to be touch on that, at least the first slide. So this is what we used to do. If you take your elementary machine learning textbook, you have your train distribution, you have a test distribution, they're equal, and life is good, and we understand a lot of things theoretically about how this works. For a while, I was pushing very hard on trying to do OD evaluation, because this is how the real world is. You train your model, you always encounter OD situations, and why not really embrace that in on the methodological side? And this is now what we're doing today with large language models. You actually, I don't know what to call it, what kind of evaluation to call it, but you train on stuff and then you test on other stuff, and the stuff could overlap. And this has been, I guess, commented on in various forms. So this is a tweet that says, GPT-4 came out, and it was amazing at this code forces problem solving 10 out of 10 on pre-2021, and then 0 out of 10 on more recent problems. So this was a bit suspicious and points to some sort of train contamination. Recently, we put out this very kind of simple position paper that says, well, if a foundation model developer is going to report some benchmark, then there should really report some sort of train test overlap, or give people confidence that they didn't train on the test set. And to what extent is that actually true right now? 9 out of 30. So this is a list of all the top language models that we could find who actually published benchmark scores, and a small handful of them did some sort of train test overlap, and the others we just have no idea. Okay, so this is sort of concerning, because as we yeah, Jacob.
There's contamination because they repeat the canary strings that they weren't supposed to train on.
So some of them you actually know that there is contamination. That's possible as well. Yeah. So we've seen this story where capabilities increase over time, but I think really concerningly is the symmetric picture where access to assets decreases over time. And we used to have papers, code, data, weights, which you can study. And now we have an API. It's a good API, but it's just an API. And so you can ask the question, why does access matter? And I want to argue that this is something that's actually maybe more fundamental than people think about. And it's because access shapes the research that you can do. So most of the time, you probably don't think about it because you just do the research with whatever you have. But there's many examples where having access to certain resources dramatically changes the nature of the research. For example, in NLP in the 90s, the access to all these corpora and data sets meant that statistical methods could actually take off. Before, it was all rule-based methods, and this wouldn't happen without data. It's sort of obvious stating it, but it's sort of worth kind of thinking about. In the 2010s, there were crowdsourcing platforms like Amazon Mechanical Turk, and this led to the rise of large-scale data sets like ImageNet and Squad and others. And that wouldn't have happened without crowdsourcing. And of course, without GPUs, we wouldn't have deep learning. So for foundation models, there's sort of 3 levels of access. Access to just a black box API, access to weights, and access open source access. And I'll explain what that means later. So at the API level, the analogy I like to use is imagine you're a cognitive scientist. You can study the behavior of a box by essentially prompting it with something and seeing a response, but you can't really look inside the box. I will say that there's actually quite a few opportunities and research problems, even just given black box access, which I'll explore, in particular, building agents that solve complex problems. if you have open weight access, the analogy is now you're a neuroscientist who can probe at internal activations. And now, of course, real neuroscientists have it much harder than we do, but nonetheless. And the opportunity here is a deeper understanding of the underlying mechanisms and the ability to create novel derivatives. Now, both of these type of accesses still leave us within the confines of existing models. And we know that with existing models, there's fundamental issues that are just unresolved. And so, for example, take this jailbreaking paper. So we know that generally, if you ask a language model to do bad stuff, it'll say, I'm sorry. But this paper shows that if you just change things to be the past tense, then the attack success rate goes up a lot. And so I bring this up as just it's 2024, and why are we still able to write this type of paper? Like it seems like something fundamentally is broken about the models if these such simple attacks kind of still exist right now. And we know that attention is all you need since 2017. But is that actually true? So I guess in less than 3 years, we'll see who loses a lot of money. But to answer to questions like these, you really need deeper access. You need to kind of behave like a computer scientist who is building a system that you can actually control, any part of it. And the opportunity with this type of access is that you can question everything. And you want to question the data, the model architecture, the training, and only then, hopefully, we'll be somewhere good. So in the rest of the talk, I'm going to descend this layer cake, starting at API access, and along the way, show you some examples of the type of things you can do with each type of access. So with API access, the way I like to think about this is the API is this quote unquote universal function, meaning that if you put in a prompt with some instructions, then that box can do various things like summarize or verify or generate. Do you have a question?
I was just wondering if you were going to alternate ways.
The question is, are there alternate ways of studying these? I mean, I guess open source is the fullest access, so anything would be contained.
So a natural alternative to study a small model, not a large model.
Sure. I guess that's sort of a orthogonal access.
We will not discuss that.
I will mention at the end. There will be some. By the time you get to open source, unfortunately, things will be smaller. Okay, but happy to discuss this later. So you have this function that can do all sorts of things, and now you can take these and compose them together to create these agents. And importantly, the API controls the execution, so to speak. It's not that you have a fixed program that just dispatches to a bunch of API calls and then you're done. It's the fact that the API can actually dictate what function you're going to call next. So here's a basic agent architecture. So the agent gets some observations. It goes into a memory stream which records everything that it's seen so far, and then it retrieves some subset of that memory stream, and then it can do one of three things. It can act in the present. So think of this as tool use, making a function call or running some command. It can reflect on the past. So this is running some sort of verification, a summary, and it can make future plans. So each of these is driven by this LM API. Okay, so given this basic agent architecture, we can build two types of agents. So the first is problem-solving agents, which if you hear the word agent, this is what most people mean. And the second is simulation agents, which is underexplored, I think, but actually quite interesting. So I'll talk about one paper that we worked on the problem-solving agent. So this is led by my student Chen, called ML Agent Bench. And the task is familiar to all of us. It's basically you're given a machine learning problem, some starter code, some data, an evaluator, and your goal is to increase the performance or accuracy of the model. So what you might do is you edit the code, you run the command, you look at the training log, and you think a bit, and then you edit the code and you run the command and so on. And now the question is, how can you get a language model agent to do this? So it's sort of interesting. Like a few years ago, this would have been like completely crazy, but now it's only a mildly crazy. So this, hopefully you can see at least some of this. This is what we do basically. So you ask the language model in the prompt form to reflect on what has happened so far, make a plan, fact check itself, and think a little bit and produce an action where the action can be edit a file or run a command. And then in addition, you give the language model a history of the last 3 things that have happened so far. So this goes into an LM. The LM produces a response with a reflection of the past, the plan, fact check, and a action. And that action gets executed, code is run, it produces some log. This log goes back into the history and you iterate. Okay, so everything is just, it's very simple. It's just, prompting the language model, feeding the history back, prompting the language model, again. And this sort of works. So we looked at 13 different tasks, machine learning related tasks, and benchmarked a bunch of different models. And the best model was Claude, and it on some classic Kaggle benchmarks, it really nailed it, and on some of the newer ones, it did not nail it at all. But I think now, since then, there's probably better results from stronger agents. Okay.
All of these are instantiations of your agent. You're just swapping out what is the base model that's...
Right, that's right. Yeah, so the agent architecture is fixed. This part is fixed, and only the model is swapped out with one of these.
Now you have like a lot of arbitrary design choices about like how to organize the agent, what instructions to put exactly. Were those optimized against one particular backend model?
Yeah, so that's a good point. So when you design this, we're using mostly GPT-4 and Claude to prototype. So you could imagine there's some non-zero amount of overfitting. I don't think it's maybe too much because it wasn't like, it was sort of still human in the loop design optimization, but it's a good point. Yeah.
Could you somehow get even better results?
Oh, the question is, can you combine these models to produce even better results? Probably. We did not try that. There have been some results like this mixture of agents work that shows if you query multiple models and synthesize the results into one action, we can do better than any individual model.
But the same could be about the prompting too, right? Combine instantiation too, even more robust and stable.
Yeah, so you could try multiple prompts as well. And that's something that, at some point it becomes more expensive. So if you did that, then you might want to compare with the counterfactual of, let's say, you just run the single agent for longer and to have an apples to apples comparison.
How much do you think this will transfer? It started by domain adaptation. And aren't you risking overfitting to the benchmark data? Eventually, say in a medical situation.
Yeah, I guess my view is now that benchmarks are sort of used once or twice almost. Like if the first time you design a benchmark, you get a fresh view on how performance is. And then it sort of gets recycled and it degrades, and then you have to get a new one. So it's almost like a kind of online learning. You test and then you train or do whatever people do.
But if you don't bring enough reality benchmark, you can keep doing that, it's too far away from reality.
Right. So there's a whole benchmark design you have to do. I mean, you see maybe some kind of overfitting because on some of these classic benchmarks, it does better than on some of the newer ones. Okay, let me move on. So there's a ton of actually exciting work in this area of research agents. And one thing I think is really cool about it is not just an arbitrary task, because if you can solve this task better, then you improve the model, and that allows you to solve the task even better, hopefully. I'm going to skip this other project that we have, building agents to do cybersecurity challenges, but it's modeled after sort of the same ideas. So let me now move to simulation agents. This is led by my student June, and the idea here is, can we simulate people in at least in some form? And so we have a little city of 25 agents. Each agent is powered by this architecture, which actually comes from this paper. I'm going to focus on these two parts, retrieval and reflection. So remember, the memory stream contains everything that agent has experienced. So we made a design decision to literally record everything that happens. So bed is idle, Isabel is stretching, shelf is idle, desk is neat. So it's a very mundane thing. Like as you go through it every day, most of your perception is just kind of not that interesting. But the problem is that you don't know what to keep and what not to keep. And we actually remember probably more than we're maybe conscious of. So that means, given all this really low-level memory, we need to be able to retrieve in a given context the relevant information. And we do that based on a combination of how recent something is, how a priori important it is, and how relevant it is to the current context. I'm going to go quickly because of time. And the other thing that we do is reflection, where, again, observations are fairly low level, like Klaus is reading about urban design. And the problem with this is that you don't want an agent to be only dependent on very low level details. So we have this reflection operation where it sort of abstracts these observations, which are low level, into higher level observations, like Klaus is highly dedicated to research. And this gives the agents sort of a general sense of purpose, like, oh, I'm dedicated to research, I'm going to go do more research, and which makes it more of a believable agent. So the other thing about people is that they are social creatures and they talk to one another. So we had agents have conversations with one another. So Isabella goes and tells people about her Valentine's Day party, and then those people go and spread the news, and then sometimes it comes back to them. So this is sort of simulating information diffusion in social networks. But one problem with this setup is that this is all sort of made up in a fictitious world. So now we can ask the question, how can we make this more real? Can we actually model real people? And so the immediate question is, how do you sort of pack a real person into an LM agent? And the insight we had here is using interviews. So we did a pilot interview with June, who's the first author here. Tell me about your upbringing and family background, and he's talking about being born in Korea and so on. And you read this thing, it's actually very rich, not just in terms of having factual content, but also you learn about June's personality, his perspectives on life, his views, and so on. And so what we do is we have 1,000 people, real people, sampled from demographic diverse population across the US. Each of them we subject to a 2-hour audio interview that produces a transcript for every person. And that transcript serves as the LM agent's memory. So now we have person and corresponding agent. Now we want to see how close the person is to the agent. So we created a battery of tests, survey questions from a general social survey, personality test, some economic games, and some behavioral experiments. And we had the real person, the human, do these things. We also had the simulated agent do these things. And then we compare how close the responses were. Okay, and the result on the general social survey is that the humans themselves are not consistent. So we have them wait 2 weeks and then answer the same questions, and they're 81% consistent with themselves. And the interview-based agent was 69% accurate. So if you look at the gap, you can think about this as capturing 85% of the accuracy from a 2-hour interview plus a language model. And some of the baselines work worse. Yeah.
The accuracy here is how consistent.
So accuracy here, so each of these survey questions is, let's say, is a multiple choice question. So it's A through E. So accuracy is basically did you get the answer correct or not? So for when you're looking at the consistency, you're looking at the accuracy of the second time. Basically the first time the agent is that's the answer key, and then the second time they take the survey, that's their prediction, and we see how accurate it is.
Intervene, things might have changed, right?
Things might have changed. I think many of these questions are meant to not be fluctuate based on your mood of day, but of course there are some completely non-random fluctuations. Yeah. So I think this is pretty interesting. And it shows that the power of language models to actually capture, to extract all those little pieces of information from the interview transcript to solve these problems. So in the language of domain adaptation, because I'm trying to make the connection here, you can think about this as training data, but training data is just like an interview, which is very unstructured, and then you're generalizing to these tests, which are these structured questions. Yeah.
Maybe the model just comes up with a generic person. I mean, the question is, do you see variance between training on different people? Because there is the variance between the people.
Right. So the question is like, what? Maybe the model is being generic. So here's some baselines. So if you just use the person's demographics, or you use basically a 1-paragraph summary of the interview, then the accuracy is much lower. So it's not 0. I mean, it's still far above random baseline, but it's the interview does seem to
Random is pick a random answer, or
random answer. Random answer.
So maybe the baseline would be nice to see here.
Yeah, that's true. Yeah. Okay, let me move on. So just to reflect on this section, API access is limiting, but on the other hand, you can still do a lot. You can solve complex problems in machine learning research. You can simulate people, which to some extent, and this is actually very exciting for social scientists, who see this as a potential laboratory or a digital twin, which allows you to run certain experiments sort of in vitro. And maybe one limitation of all of this is that this is still at the end of the day, prompting, right? We have these static agents that, and we really want them to be able to learn from their experiences. And for that, you need to go beyond black box access. So one analogy is, if you think about how AlphaGo worked, there was this initial supervised learning stage where you're training on human labels, essentially, or predictions. And then there's a reinforcement learning phase. And we're sort of at this point where all the language models we have mostly are just trained through imitation learning on human-generated text. And with agents, there's a possibility of putting them in complex environments, getting some sort of reward signal, and bootstrapping up something more powerful. Okay. So let me talk about open. How much time do I have? Okay, 12 minutes. Okay. Okay, 15. Wow, so generous. Okay, so let's descend the layer cake to open weight models. So technically, these should be called dual use foundation models with widely available weights, which comes from the executive order from last year. And the reason they're widely available as opposed to universally available is that, yeah, it just rolls off the tongue. Is because there are restrictions. If you happen to be an organization that has over 700 million active users, then it's not actually open to you. So just a caveat. But for the rest of us, it is freely available to use. One advantage that you get from open weight models is off the bat is reproducibility. So I don't know how many of you have used Text DaVinci 003, like OpenAI model. So some of you. Well, too bad it's gone now because these API models get deprecated, so which means that any of the results from back then you can't replicate anymore. Whereas if you had open weights models, then you just always have the weights on your hard drive, or as long as Hugging Face is still there, you can download them with Hugging Face. There's a lot of research that's opened up by open weight models. So we've had a paper on the topic of open weight models from last year. I want to highlight a few kind of types of research that can be done with open weight models. The first is what Jacob already talked about this morning, so I won't go into that, but all of transluce depends on having open weight models. I'll just say that. The second category of things is interesting. So this is a paper from NVIDIA where they took a 15 billion parameter model and they pruned out some of the layers, and then they fine-tuned it a little bit more to fix it up. And they were able to get 8 billion parameter and 4 billion parameter models that were pretty strong. So more generally, this is, I think, a nice area of research where you can take models of one form factor and convert them into a different form factor, usually a smaller one. This is a cool paper where they were able to optimize a prompt using open weight access, because you need to go through the gradients of the model to generate a adversarial attack to jailbreak a model. And then the surprising part is that they were able to take the exact same prompt and jailbreak OpenAI closed models. And this says that open weight models actually tells us something about closed models as well, because of this mysterious transfer, which we saw with adversarial examples in images, but it seems to be a much deeper phenomenon. I'd be curious what's going on here. I want to spend a little bit more time talking about one of the projects that we've been working on with my students, Sally, Ahmed, and Rohit. And this is a project that is not just using open weight models, but is motivated by open weight models. So the motivation is that you go on Hugging Face, there's a lot of models out there. And some of these models are fine-tunes of the same foundation models like Llama 3, and some of them are not, or at least they claim they're not. And so the question is, or the goal is to understand what is going on in this crazy open weight ecosystem. And so the concrete question is, if I give you two sets of parameters, theta 1 and theta 2, can you tell me whether these two were independently trained or not? And in the not case, there's many things that could happen. Theta 1 could be fine-tuned from theta 2, the reverse, or they could be fine-tuned from a third model. They could be all.
Like OpenAI model, that someone generates some corpus in part by getting outputs from a model, and it essentially one model is like a distillation, or to some degree a distillation of the capabilities of another. Are you accounting for that?
I would say those are independently trained. I would count that as
even if trained on the same data set.
If they're on the same data set and they're actually independently trained.
No, independently, even if one is trained to clone the behavior of the other.
Under my definition.
Starting from a random initialization.
Yeah.
Okay.
So here, I guess you have to ask like, what is the random variable here? And the data is not random. I'm assuming basically it boils down to, just to jump ahead a little bit, the initialization and the data ordering is the random variables, and I'm asking whether those sorts of randomness are shared or not. Okay, hopefully this will become a little bit clearer as I go through this. So one idea is you just compute some sort of similarity metric. Let's just take these two weights and compute like cosine similarity of the MLP weights, and you get some number. The problem is that, well, if you get 0.1, does that mean they're independently trained or not? I don't know. I mean, is that large? Is that small? Does it matter how long you've trained? If theta 2 were fine-tuned from theta 1 for a very long time, does that mean I have to use a higher threshold? But I don't even have that information. And can you get any sort of robust statistical guarantees?
Like permute the weights and get a completely different answer out, which doesn't seem to like that should matter for like the notion of independence that you seem to care about.
Yeah. So you're right. That I'm not actually going to address in this talk, but I'll revisit that at the end. So here's a second idea. This is not a practical algorithm, but it will help us think about the problem correctly. So suppose we knew how theta 1 was trained. It was trained through some random initialization and through this train function. And so, let's just train a bunch of clones of theta 1, which are all independent of each other through this random initialization. Again, the data is fixed, so I'm not, I don't think of that as the random variable. And so the intuition is that, well, if theta 2 were genuinely independent of theta 1, then this similarity shouldn't look that different from the similarity between theta 2 and any other random clone. Okay, so this gives me a natural way to get a p-value out, which is I look at the fraction of times this sort of independent trained model was in terms of similarity was more extreme than what I observed with a similarity between theta 1 and theta 2. So that number is, if that is very extreme, then I say that, well, probably I can reject the null hypothesis that they're independent. Okay, so the problem is that you can't actually do this because I don't know how theta 1 was trained. And even if you knew how theta 1 was trained, you don't want to spend millions of dollars retraining this just to do this simple test. So I guess the key is that you don't have to do this. So one intuition is that, well, instead of retraining from scratch, what if you sort of fake it by just permuting the hidden units defined by theta? So in this case, it means like for some of the matrices, you just like permute the rows. And then you do the same thing, except for instead of retraining, so you look at the permutations. So this basically gives you a set of models which could have arisen from this process because of the in the invariance to order that was actually alluded to earlier. So if theta 2 were really derived from theta 1, let's say, then by permuting it would be it would look kind of very, very different. Okay, so now I think the question from earlier sort of preempts this and says, well, I'm a clever adversary. If I know you're going to do this, I'm just going to permute the theta. So this test won't work for that. In the paper, we have a robust test which does allow you to handle the permutation. It's we don't get exact p-values in that case, and it's also a bit more specific to the particular type of MLP. But it is a thing. We can talk about that later. But let's stick with this sort of a simple case where it's not robust test. So empirical validation. So we looked at the part of the models that we understood based on public documentation, and we found that the models that were supposed to be independent, the p-values are indeed fairly uniform-ish, whereas the models that are not independent because they were fine-tunes of Llama, the p-values are minuscule. So this test empirically works extremely well. We also looked at some fun findings. So there was this controversy where this mysterious model of MICU was leaked, and people thought it was a fine tune of Llama 2, which came from Meta. This was verified by the Mistral CEO, but we were also able to independently check that indeed these two models were not independent. So two other models, Striped Hyena took a Mistral and inserted some other layers. And we were able to check that those two models were indeed not independent. So this technique doesn't have to assume that the models have the same architecture. And finally, Meta announced Llama 3.2, a 3B model, which they describe as coming from a 8B Llama 3.1. And we sort of verified that that was indeed the case, meaning that the two were not independent. What's actually interesting about this is that the technique actually gives you finer resolution. It tells you which layers came from which other layers, which is information that was not revealed in the blog post. Okay, so reflecting on open weight access. So clearly these open weight models have been immensely valuable for research and allow for reproducible research on interpretability, fine-tuning, distillation, model merging. I think one thing that they're sort of really trying to dig into is you're looking at the weights and you're trying to change them or reason about them. But it's sort of an open question how this corresponds to coherent functional changes in the model. If I just lop down a layer, that's not really a sensible thing in terms of semantics of the function. But somehow this still is a reasonable thing to do empirically. It teaches us about API models, and it also introduces new types of problems, such as this model independence testing problem that I spent some time on. But we're still confined to the blueprint of existing models, still Transformer, still Llama. And in order to go further than that, we need to go to open source models. And I have like, what, 2 minutes? 2 minutes. Okay. So speeding through this, the good news is that there are a lot of open source language model efforts out there. The bad news is that all of them are very far behind the open weight models and the closed models. I'm going to skip this open source section, but the term open source comes from open source software, which has this long tradition of people who are interested in creativity, exploration, transparency, and so on. There's a definition now for open source AI from the open source initiative, and it requires the release of parameters code, which includes all the data processing code as well. So that's something that often gets neglected, and people ask, well, like, why is Llama not open source? And it's because of, well, many reasons. And then data information. So it's not required that the data be released openly. And this is because, in short, you don't want to get sued. Another thing is that you would ideally like the compute to be able to retrain models, even though that's not strictly part of the open source definition. So I'm going to skip this. There's a bunch of projects that we can do once we can actually train from scratch, different architectures, different training algorithms, different ways to select data. There's a question of what happens if you scale up. So the compute that's available to people who are interested in open source is a minuscule fraction of what, let's say, OpenAI has. So what happens when you scale up? And here's 3 answers to that. One is that, well, you don't scale up, but you put your scaling hat on and you say the word scaling laws. So scaling laws generally are about seeing how far you can extrapolate to larger and larger scale, right? But you can go in the other direction and ask, are there things at small scale that, ablations, different data, different things that you can do, which actually translate to larger scales? And this is kind of an open research problem that would, I think, unlock a lot of research on language model training, because then people could work on small scale, but still have the confidence that this is, meaningful. Second is that there's GPUs actually that are idle in a lot of places. If you can only put them together, you can actually do some more serious training. The problem is that the interconnects are really bad across, from outside the data center, like 100 times worse. We had a paper that shows you can actually circumvent some of these, and this has been followed up. So now there's this basically decentralized training of a 10 billion parameter model that's happening through various kind of GPU donations. So that's another thing you can do. The third thing is that you can ask for more money. So I'm not sure this is gonna how well this is gonna work these days, but there was a snare pilot, which was this effort to try to fund public AI research, and hopefully, fingers crossed that this is gonna continue. But if you look at the sciences, there's this kind of long history of scientists deciding that a problem was important enough and you need to build a research infrastructure so that you can unlock all the science. And I think this is something that we're kind of missing in AI. So with that, I will conclude. Thanks.
Time for one question or two. And also, there's a panel after the next talk, which is the last talk. So give a chance to, first part of the panel, so a chance to ask a question. Go ahead.
Just a simple question. Are there examples of scaling laws?
Are there examples of scaling?
I couldn't understand. Was that something you saying it would be nice to have?
So the question is, are there scaling laws? There are papers that say there are scaling. I mean, there are scaling laws, but the problem is that a lot of the scaling laws don't really work that well at very small scales, like hundreds of millions of parameters. But I mean, I'm not sure if there's like more I should read into the question, but we could talk offline.
They're not rigorous, if that's what you're asking.
That's what
Yeah.
Okay, that's what I thought you were asking.
The question whether the use of the word law is justified.
Yeah.
I wasn't sure how much to.
Empirical.
Yeah. There are empirical curve fits. Yeah.
I had a question about the independence test.
Yeah.
How much of the success do you think depends on the fact that that was a 70 billion model? Because the smaller models tend to have a more generalized way that they memorize in. So I wonder if that was like a 7 billion or 1 billion model that was fine-tuned. It might have been harder to capture this.
So
I'm saying it's based on membership inference work that we've been doing. It's like much harder.
So most of the experiments were on 7B models, and we also tried some of the 3B models. So I mean, I think if you look at the p-values, they basically underflow. So I'm pretty confident they will work on much smaller models as well. Like this is like a surprisingly robust thing. Like we tried a bunch of different statistics. We didn't have to take all the layers. We only look at the MLP. We just ignored all the transformer blocks, and you can take like a subset, and like a lot of things work.
All right, great, thanks.
Okay, thank you.